wheel radius of R1 is 0.8 meters. This is the wheel radius, and hub of radius of 0.4 meters. So this is the 0.8 and this is 0.4 meters. It's shown in the diagram. Two masses are hung from the wheel hub system. The mass M2 on the left is hung from the hub. The mass M1 is hung from the wheel. The system is in equilibrium. The system is in equilibrium. The moment of inertia for this hub system is what it is. That is not important for this moment. Which of the following statements is true? What is bigger? First assignment. What is bigger? M1 or M2? Are they equal? Or is there one bigger than another? In the state of equilibrium, there is no motion. This thing resembles very much to seesaw, and you have some practical experience with the seesaw. M1, okay, here is mass M1, and here is somewhere mass on the half of the way is somewhere mass M2. And you know from your experiences when you were a child, the bigger you are, you need to move closer to the pivot. So if you have a very light friend, he will have to go on the back, and if you are heavier than him, you will have to sit closer to the pivot. That is just it. So what is the larger here? What is the bigger mass? M2 is bigger than M1, and you know that from experience. Very similar to this situation here. Okay, so answer for this question here would be this. Answer is under B. M2 has to have a bigger mass for the system to be in equilibrium. The mass of M2 is 1.6 kg. What is the mass of M1? If this is 1.6 kg, what is the mass of this? On a halfway. So we will see what will be. Okay. Let us start from the first question again. So I did give you some answer, simplified answer here, and now let us do that same thing throughout the equation. So for the system to be in equilibrium, we need what? We need the sum of the clockwise torques to be equal to the sum of the counterclockwise torques. And the clockwise torques is the weight of the first mass times the lever arm of the first mass. That is a clockwise torque. So clockwise torque, it's equal weight of the first time R1, that is distance from here all the way to here, from here to here, and that is M1G times R1. That is a clockwise torque. Anti-clockwise torque, it's similar but with different, and that is M2 times G times R2. Okay. But I here put R1 is 0.8 meters, R2 is 0.4 meters, and 1 is some unknown mass, and 2 is also unknown mass, but I placed here as a multiply of the first mass. So it will always have some relationship. Let us return to the equilibrium situation. So clockwise torques will be equal to the counterclockwise torques. In that case, this is the clockwise torque, this is the mass, this is the gravitational acceleration, that means this is the weight of the first weight. This is the lever arm, so distance, it's radius of the cylinder or disc, whatever it is. And this is the mass, the gravitational acceleration, this is the second mass, gravitational acceleration, and the radius of the hub or the lever arm of the second torque, for the second torque. So G, we have G on both sides, so we could subtract that, divide both sides with G, and G will become 1, so there is nothing there. And we could rewrite the equation here, then this equation we can rewrite as this one, and this one we could rewrite as this one. So we divide both sides with the R2, and again we do M1. So we will get this equation. R1 divided by R2 is equal to the M2 divided by M1, and that is essentially some unknown magnitude, as we noted here. In this specific situation, M2 divided by M1, you see that it's a relationship like R1 divided by R2, and R1 and R2 is 0.8 divided by 0.4, and that is 2. That is just number 2. In other words, for equilibrium mass M1 is 2 times smaller than mass M2. So, for this system to be in equilibrium, this mass has to be 2 times smaller than this mass. And this is from your experience. So if you have 50 kilos, your friend will have 25 kilos, and you will be on half the way to the pivot point S. And he will be at the end of C. So that was the first assignment. Second assignment, if you assume that the system is in equilibrium and the mass M2 is 1.6 kilograms, what is the mass M1? Okay, that is simple calculation, M2 divided by 2, that is 0.8 kilograms, so exactly half. And for the third assignment, it is the most interesting one. If the M1 is 0.88 kg, is large enough for the system to rotate, when M2 is 1.6 kilograms, so you see, this is not exactly 2 times, this is slightly larger than a 2 time, so it will go downwards in this direction. And we need to find acceleration on M2, so we need to find linear acceleration on M2. M1 will go downwards and M2 will go upwards, of course, and it will have linear acceleration of A2. For that we need two equations. First equations will be, this is the net torque, next external torque, this is the moment of inertia, this is angular acceleration. This is first equation. Second equation is linear connection between linear and angular acceleration. Linear acceleration is A, this is the radius, and this is the angular acceleration. So this is very similar to second Newton law. When we have straight motion, when we have straight motion, then force is equal mass to the acceleration. See, force, this is the torque, and this is the mass, and here is the moment of inertia, this is acceleration, this is angular acceleration. So that is, if you have trouble remembering this, you could remember this. So we have everything that we need, and for complete written answer, please follow the link in the description. If you want more of this, please subscribe and tell your friends. Bye.